In our last lecture, we saw that there's a sharp rise in average global temperature. And the primary cause of that sharp rise is a phenomenon called the greenhouse effect. And by the way, the term greenhouse effect was introduced 200 years ago in 1820. And it's not technically accurate. They didn't understand the physics as well back then. A closer analogy is that these greenhouse gases, which we'll talk about, act like a blanket. So this blanket of greenhouse gases traps infrared radiation from the sun and keeps it from escaping, holds it to the surface of the Earth, which heats up to restore an energy balance. Carbon dioxide is the most well-known greenhouse gas. There are a number of others. Well, the most abundant gases in our atmosphere are nitrogen and oxygen, and they are not greenhouse gases. They are simple molecules made of two atoms each, N2 and O2, and because of their simple shapes, they don't block much outgoing radiation. Greenhouse gases are molecules that are larger and more complicated. The most common ones are water and carbon dioxide. Water does not stay in the air for long. Carbon dioxide does. These are larger molecules made of 3 atoms each, and because of that shape, they have more ways to rotate and vibrate, and in many cases, they happen to vibrate at the frequencies of infrared radiation. Then some greenhouse gas molecules have more than 3 atoms, so methane is an example. There's a monitoring station high up on the Mauna Loa volcano in Hawaii that has been sampling clean Pacific air and recording carbon dioxide levels since 1958. And you can see a graph here showing those concentrations. Now you notice there's kind of a zigzag shape. I don't know if you can guess what's causing that. It's how plants grow and go dormant summer and winter. So sometimes they take in more carbon dioxide, sometimes they put out more carbon dioxide. But you can see the overall pattern here. It's been rising since measurements began. And we know that carbon dioxide and temperature are connected. Carbon dioxide concentration is measured in parts per million. During the ice ages, carbon dioxide was around 170 parts per million. In between them, and at the start of the Industrial Revolution, it was around 280 parts per million. Today, the concentration is 414 parts per million and going up. Scientists worry about causing a tipping point in the system. They used to think that 450 parts per million was a safe limit. Our science has gotten more detailed and more robust, and now we understand the safe limit to be 350 parts per million. And we're above that now. Well, what can we expect in the future? Scientific data tell us some things with a high degree of certainty. And we can see that some of these things graphed here. Rising temperatures, rising sea level, melting glaciers and melting sea ice. We also know with a great deal of certainty that there will be heat waves, droughts and mega droughts, wildfires, more extreme weather, habitat loss, food insecurity, health issues, social impacts. And then feedback is a circular mechanism that we're a little bit concerned about. It can be positive or negative. A positive feedback loop amplifies the original change. So for example, as the climate gets warmer, you can see these 3 things here are views looking down at the North Pole in 1885, 1985, and projected 2085. So as the climate warms, it melts the Arctic sea ice, And now instead of white ice, there's the darker colored water. It absorbs more sunlight, which warms the air, causes more sea ice to melt, and around it goes. So it's not just the gradual warming of the planet that we're concerned about. Systems scientists are also concerned about tipping points. Methane, you probably know, is another potential positive feedback loop that we're very concerned about. We have what is called climate commitment. And what that means is we're committed to a warmer climate because of the carbon dioxide that's already in the atmosphere. In fact, the warming that we're experiencing now is, in fact, due to carbon dioxide levels from the previous century. Even if we completely stopped burning fossil fuels tomorrow, the planet would continue to warm for several hundred years because of the greenhouse gases that are already in the system. Nevertheless, there are grounds for hope, and that's why we're looking at green buildings this term. If we are very committed soon enough to avoid tipping points, the climate will eventually stabilize and the carbon dioxide concentration will begin to fall below 350 parts per million. At that point, assuming geochemical cycles, remaining ecosystems, and other planetary components have stabilized, the parts of the Earth system that survive will be able, slowly, to soak up the excess carbon dioxide and restore balance. However, much will have changed. Earth, when it settles into a new state of dynamic equilibrium, will not be the same as it was before. Between now and then lies the transition. That is where we live now. The transition back to stability is likely to take centuries, and scientists tell us that the climate impacts of fossil fuels are expected to last at least hundreds, probably thousands of years. The work we do now is for a future we will never see. How do green buildings fit into this picture? There are two kinds of responses to climate change. One of them is adaptation, which means, okay, you've got some climate change, that's what you've got. How do you manage and adjust to the impacts of what you've already got? Then mitigation refers to trying to limit future climate change by reducing or preventing the emission of greenhouse gases. And that is our focus. The way we build our buildings has a big role to play. And next week, we will start looking at how to do that. Here are some sources for you. Here are some books. Most of these are in our library. Here are some websites. And now I want to show you, here's the Ipcc, and I want to show you where you can find those Ipcc reports. Here is the Google shared drive for our course. Here's Sustainable Building Systems right here. You're familiar with this. And here are our lecture folders. You'll remember that they're subdivided by general topic, so we've been in the overview section here. We've been looking at these PowerPoints. And you'll also remember that in many of these lectures folders, I've put extra goodies for you in this subfolder called Articles and Extra Resources. If you click that down arrow, you will notice that I have put some subfolders with Ipcc in them. And I downloaded these for you because, as you will see when you look in these, the amount of material here is really vast. So here's this 2014 report, and it's divided into several sections. This first report is about the physical science, the basis of the thing. They have many chapters. They discuss the scientific basis, and you can read as much technical detail as you want. You can also, I find these helpful, go to the end and look at the summary for policymakers. In other words, people in government who are writing laws, they don't have time to read all these reports, so they can go look at this summary. And then they also provide a technical summary where you can just read about the science details. So there are report files for each of these. Here's one on impacts, here's one on how can we do mitigation, and then here's one on a synthesis and some more general information. Then I mentioned there are some special reports. Here's the special report from 2018. Here's I think that's the one that talks about the cryosphere and land. Then here's the 2019 report. It talks about land and especially desertification and about food supply. So anyway, here you go. Here are many Ipcc reports for you in this folder that says articles and extra resources. So I hope you find those useful.